Hey, welcome back. Good to see you again. Thanks for joining the channel. Today on the bench I have a Citation 12. This old relic has been waiting a long time for the bench. And I did feature this in another video earlier. I think it was last year. I pulled it out to do a test. I used it as a test amplifier and I plugged it in and tried it out, and it wasn't doing too good. It had some serious DC on one channel, I think, and it was having a fit. But we're going to do this today. I got a few plans for this as well, modifications. I'm kind of curious as to how this one goes. This is a very early solid state amplifier for Harman Kardon, the 12, and it's got limited power too, 60 watts per channel, and it's got some really good design features on it, some not so good design features. And but a lot of people rave about these amps. On the back you got nothing. It's just plain power cord coming out, that's it. The sides, nothing. On the front, I guess they call this the front, you have your heat sinks, input left, input right, output left, output right, fuse for each side, and a power lamp for the unit. And it's kind of a monoblock design. It has pretty much everything separate. It's got two power supplies and of course two amplifiers. Before I connect this up and try it out, plug it in, try it out, see what it's not doing right, we're gonna have let's have a little look at the documentation for this. So here's a look at the power supply. The power comes in and it's a pilot lamp with a dropping resistor. It's a neon bulb. And then it goes to two transformers. Each transformer has its own fuse and circuit breaker. And I'm not sure why they do that. I think I'll probably just eliminate the circuit breaker and just go with the fuse. I don't know if there's no advantage to having both, unless this is a lower current and it trips before the fuse blows. But that's only 3 amps, so. Anyways, transformer looks like it's wired for 110 and 220, and you can reconfigure that down here. Down here it shows you how you can reconfigure it. And then it's pretty standard, a very bridge rectifier, a ground reference resistor tied to the center tap of the transformer. There's a 10 ohm resistor, earth reference, and then this one here is directly tied to earth. So they're keeping a little bit of resistance between the two. 6,000 microfarad 50 volt caps, and then that's your power supply, plus and minus 42 volts. Here they talk about a board revision, either type 1 or type 2, and the only real thing I see different here is right here they have a 12K resistor, and here's an 8.2K. Everything else is the same. I guess the older versions used a special dual transistor, and then the later versions they use separate transistors. So maybe that's what the only revisions are. Everything else looks the same. Schematic, it's a fairly simple design, and from what I understand they took this right out of the RCA transistor handbook, and I don't know if they modified it any, but it's pretty simple. Got your input differential pair, pre-driver, bias, and then you have a driver here, and then your outputs. So very minimal parts count, a very simple design. This is your output here. Let's see, output goes through 0.27 ohm resistor, 0.27 ohm. Okay, so this is our output. And then they have a circuit breaker before it heads out the back, or at the front. One thing I propose to do is put active speaker protection circuit in this to have a relay on the outputs to relay switch the outputs on and off and provide protection. And it looks like the only power that supplies is plus 41.5 and minus 41.5. So we're going to have to do something with finding a way to get power to that little circuit I'm going to install. So we'll talk about that later. Another thing, this is a scan of, I think this manual, this service manual came from Hi-Fi Engine, I'm not sure. But they have this, somebody drew this picture here. And it shows a couple transistors, 4 diodes, 4 resistors. So this is some kind of a bias spreader circuit. I'm not sure. But this is our bias diode here. And this will be mounted on the heatsink. And then it comes back to the board by pin 23 and 26. So I want to look more into this. I don't know if this is a factory mod that they recommend or what. So I'm gonna research more into this, see what that's all about. We might do this if I read about it and it provides some kind of advantage. If not, I'll just leave it stock and we'll just go with it, see how it runs. Alright, wired in to do a power test. Now, one of the things I don't like about this amplifier, it has no power switch, which means you have to plug it in to turn it on, which is kind of stupid in today's world. I think it's illegal. I don't think you can build any kind of piece of equipment, commercial equipment, and without a power switch on it nowadays. I don't think that's allowed. So I'm going to put you up on the scope. I have my load connected. I got a signal source. Turn it on, and we'll turn this down to 0. We'll start off, and then we'll plug it in, and we'll see. I'll put you up on the scope, and you can watch as I plug it in. Okay, here we go. Consuming 26 watts, and we have nothing on the output. We didn't have any bump or anything. So let's turn up our signal. Turn this down. Our rate channel's twitchy. Looks like we have a problem with the rate channel. The bottom trace. So I'm going up and down in amplitude. In full power. You see we're getting some kind of noise spikes on the rate channel. Let's turn it down a bit. Right about there, I guess, would be clipping. Let me measure, see what our output is. Our rate channel, it's 25 volts. Left channel, 24.77. It's actually working better than I expected. Except we are getting, I start banging on it. Oh, seems okay. So we're doing full power, we're consuming 237 watts. I'll let this go for a while. Okay, here you're looking at, I turned up the gain of the scope. Here we're at 50 millivolts of division, and you can see on the bottom trace some spikes of noise. Things aren't stable on the rate channel. Just going to let this cook for a while. I got no signal in it right now. It's just sitting idle. And yeah, we have a lot of noise being generated in that rate channel. Just going to sit and monitor this for a while. I'm just going to check for DC offset here on the outputs. This is the rate channel. We've got about 108 millivolts. Steady. Sort of steady. It's jumping around a bit. left channel, 155 millivolts and steady. So we have some offset. Distortion reading at 1 watt is reading about, well, it's fluctuating. It's coming up and down, 0.009 to 0.01% THD. You see it's fluctuating. If I put filters on, let's put a low pass 400 hertz filter. Drops quite a bit. A little bit of hum, I guess. Well, maybe not. That's me touching the machine here. I'm inducing hum into it with my body. So we dropped to 0.0075 or so. 30 kilohertz filter drops it to 0.0038%. So that's just noise we're picking up. If I take the noise out of the equation, we're getting quite a low distortion, 0.003% or less, or 0.004% or less. That's the left channel. Okay, let's try the right. Here's the right channel at 1 watt, and we were getting some twitchiness. You saw the needle jump. There it goes. So we definitely have a problem on that right channel. So right now we're reading 0.009 or 0.01% distortion with no filters. If I put the filters in, it drops to pretty much the same as the other channel, 0.004%. But we are getting a twitchy noise on this channel. See, it's every so often it twitches. Now I noticed that when I put the amp on full power and warmed it up a bit, when I warmed it up, it seemed this twitchiness seemed to go away a bit. So that might be a failing transistor. Well, it could be anything. It could be a solder joint too. We don't know until we get in there and start doing something. But it is definitely, that rate channel definitely has a problem. Alright, so the only way in through the bottom plate, and it looks like somebody got these from a hardware store and glued them on translucent. They're not even sticking. Kind of a, yeah, and they worked, but I'm going to have to put screws to hold them down. Now we got, what, 8 screws here, 7 screws, and they look like they're all different. Got computer screws, computer case screws. We've got, yeah, it's all different stuff here. And then we got duct tape residue in the bottom. I have to remove that. So let's get these screws off, and then have a look inside. Somebody's been in and out of this girl quite a few times. This one here is buggered up. Let's get a new screwdriver. Let's get a flathead. It's cross-threaded or something. It's a machine screw. Some of these are machine screws, some of these are self-tappers. So yeah, wasn't too much care put into this thing. Get rid of all those. And the big reveal. Oh my goodness, look at this. Fubao. F-U-B-A-O. Cap. 6800 microfarad, 63 volts. Somebody ditched the original capacitors and put these things in, these Chinese junk. And they kind of zip tied them all together, and I guess it's okay for, yeah, well, it was doing the business. I know it was, because we had it on the bench and we tested it. But I think I'm going to go back to more original style cans. Problem is the clamps, the capacitor clamps are missing. I think somebody also replaced this bridge rectifier. It doesn't look like it's the original. This one looks original. This one does not, which is fine. But I think I would wish they would use some compound on there to get better heat transfer, and then tighten the screw properly. So yeah, this here I don't know about. Let's see what capacitor they have in stock. I could probably buy some caps. I still have 4 of those 22,000 microfarad left over, but that would be overkill for this thing. Probably only needs about 10,000. The originals were 6,000. Somebody put 6,800 in, and I could probably get away with 10,000. How are these things mounted? I think they're screwed down. Somebody put some glue on it too, some kind of black adhesive. Interesting. Let's take the lid off. Taking the lid off, you got to remove 4 screws. 1, 2, 3, 4. So I'll get those screws out, and then we'll have a look at the internals. Alright, the screws are out. Look at our lid. We've got some heat zones here where the dust collects. What if you have a component that dissipates heat, you get air circulation, local air circulation at it. And what it does is it picks up dust in the room and it deposits in on the top of the lid. And anytime you see that, you can know you got a heat component, because it's the heat is causing a convection. Alrighty. Somebody's put new caps in this thing. Got Elnas on this side. And we got a mishmash on this side. We got Daewoo, and these are Macrons. What else do we got here? Transistors. They look like they're all originals. RCA originals. Which is good. Those 2 little glass bulbs down there, that's the circuit breakers. And they are enclosed in a glass bulb vacuum, I think, to make them more reliable. And if the contacts are in a vacuum, then the less tendency for it to arc, and pitting is less, and oxidation of the contacts is less. So that's what they're doing there with that. And they look like light bulbs, but they're actually little thermal switches. And if too much current goes through, they warm up inside, and then a bimetallic strip opens up and the contacts open up. And this here looks pretty cheesy. Let's get rid of this. Somebody put a little effort into it. Yeah, that's exactly what I thought. Somebody just zip tied these up. But hey, they did the business. I think it was working. So our PCB boards, there's only one of them, one big one. We can remove that. We can service it separately. I want to see. Somebody's been monkeying around here, changing transistors. It's got the original dual package long tail pair transistors, Motorola's. There's a Motorola there too. These ones here, I can't even read them. There's no part number on them. And these are all originals, which is good. Not too much work's been done on this. Here's a look at the main board. So we got all original silicon, and This one's original, this one's original. Original diodes, original resistors. The caps are a mishmash of different things. So we got Daewoo caps here, Daewoo cap, Macron cap here, 100 volts, 100 volts. Another Daewoo cap here, and then we got a Nichon Chemicon, 25 volts, 220. This one here. But if you look at the other side, you got a Nichicon 220 at 16. This is a cap salvaged out of some vintage equipment. Look at the size of this 16 volt cap. Look at the size of this 25 volt cap. So you can't tell me that it was a new cap they put in there. If it is, it's probably 40 years old. And then we got Elnas here. These three are Elnas, and they're all 50 volt caps, but they use hundreds on this side. I don't know why. So it's a mishmash of things. The soldering, well, it looks okay. I don't see anything wrong with it, but it's very dirty. Like, you can't really inspect this because all the flux that's on it. So this will clean up nice. Original transistors, the original drivers. I don't know if there's any advantage to upgrading those. I don't know. I don't think so. It was working great when I plugged it in. Carbon comp resistors, I'll have to check all those for value and replace as necessary. There's quite a few of them on here. Here's a look at the board. But this is all easy stuff here. And then just cleaning. Alright, let's talk about the speaker protector circuit that I'm planning on putting in this amplifier. Now I'm going to go with a PC1237H chip. This is a protector IC for stereo amplifiers. This chip is used in a lot of commercial amplifiers, receivers in the 80s, and it's an all-in-one solution for doing speaker protection on an amplifier. What it does is it sits on the outputs of the amplifiers. There's one for, let's see here, let's see if we can find a schematic. So these are the two outputs of your amplifiers. You have one, your left channel and your right. And it picks off at the center point of your output devices. That's your speaker output. That's where the line that runs out to your speakers. It picks off the signal here and it monitors it. It goes through these two 56K resistors, and then it goes through a capacitor that removes all the high frequencies up over probably 1 or 2 hertz, and then it inputs it on pin 2. On pin 2, let's see if we can find a block diagram here. Pin 2 is your output offset detector. So if there's any DC shows up on pin 2, other than over a certain threshold, it triggers. And what it does is it shuts off the relay. And we want to protect our speakers from this amplifier because it has no protection other than those 2 circuit breakers I pointed out earlier. So we're going to pick off a signal off the outputs of the amplifiers. The circuit here, this chip is going to protect it, and it's going to run this relay, which is going to toggle all of the outputs on and off. Now, you can buy these kits on, I bought this one on AliExpress. It comes with a board. I don't know if you can see that. It says XY Hi-Fi version 1.1. I don't think you need to get this one exactly, but it's pretty basic. It's just a board that's going to hold your chip. It's going to hold your resistors and your caps, and your relay fits in the center. Here, let's just dump this all out. Your relay is going to fit here, and then your speaker output terminals are here, which is, in this case, is not ideal because they're assuming that you're going to connect it. Let's see here. This is grounds. Yeah, this is grounds, and this is your outputs. And then this is your input from your amplifier, left in, right in, and ground. So these are your inputs, and this is your outputs. No mounting holes, which is kind of, I could probably drill a hole here over this XY and use that as a mounting holes. The board's very light, doesn't use anything. So I think what I might do is use this board, but we can't use it in the way it's configured right now, because if you look here, it says they're assuming you're going to input AC 12 volts for the power. And what they're doing is it goes through this single dial, this 4007, and then it goes to this cap, which filters this power supply. And they're using that assumption that you're going to connect 12 volts AC. Now, you can connect this up to, let's see here, it says works stable with a wide power supply range of 25 to 60 volts. I measured on our amplifier and it's 44.2 volts. That's our rail supply, and that's what I'm going to pick off and use. So that's right in the middle of this 25 to 60 volts. And then you can, this is a 12 volt relay, I believe. HF14FS212D. It doesn't say 12 volts on here, but I'm assuming it is. What I might do is I might substitute in a 24 volt relay. Reason being, it has a lower operating current. A lower operating current means less drag on the main power supply, less parasitic drag. This 47 ohm resistor we're going to have to adjust, because what we want to do is we can't exactly put 44 volts across here and expect the currents to be correct. The currents will be a lot higher because the voltages are higher. They're assuming that this is going to be run off AC 12 volts, half-wave rectify it, and you come back with, I don't know, what would be here, 15 volts maybe. So this 47 ohm resistor would be correct for this AC 12 input. That's what I'm getting at. But we're not going to input AC 12 volts. We're going to input 44.2 volts DC. So we got to adjust this resistor to lower the current. Otherwise we'll burn up our coil in our relay. So we need to do some math on that. Here it says relay driver, and the maximum current for this relay driver is 80 milliamps, which is pretty high. So if we do the math, let's just assume that we're going to go with 44.2 times 0.08. That's 3.5 watts if we have 80 milliamps on that current at 44.2 volts. So we're going to have to turn this down. You know, that's my point. That's what I'm getting at. So let's figure out what we're going to do here. We know our supply voltage. We can run with this relay, and we'll have to figure out a way to turn that voltage down, or current down. Another thing is these caps. These are Chong X caps. 100 microvolt, 50 volt. There's two of these. I might use them, I might not. I don't know. I'm going to check their... There's a 22 microfarad at 100 volts. Pin 7 is your power on mute, which gives you your delay. When you first turn it on, you're going to have a few seconds delay. So they're setting it with this 22 microfarad cap, and we can change this cap to increase that time or decrease it depending on how we feel about it. Let's look at the current for the relay driver. Okay, I got 12 volts on the supply. We're going to test this relay, see what kind of current it needs at 12 volts. So I got my ammeter here. Let's connect this up. Quick and dirty. We'll see. Let's measure what current for 12 volts. So click this on. And what do we got? We got almost 44 milliamps. Okay, 43.8. Let's put that 43.8 milliamps at 12 volts. Let's take a 24 volt relay and let's check this. Let me turn up the voltage on the power supply. Okay, I got 24 volts there. Let's connect up our power, and let's test this relay. 22.1 milliamps at 24 volts. Now the reason I'm doing this is I want to see if one is more efficient than the other. So we go to data sheet, and it says here how to make it work within a wide range of power supply voltage. Pin 8. Okay. It says by choosing proper resistance R8 connection to pin 8, the IC can work within a wide range of power supply voltage, VCC, from 25 to 60 volts. In case that pin 8 is directly driven by a regulated power supply, set V8 to 3.4 volts, typical, as this is a choice of R8 value. Refer to the characteristic curve of shown in figure 6. So if we look at figure 6, here's figure 6, optimum value of external resistance of R8. So here's our power supply voltage. It is 44 point whatever, 44.1. Let's just say 45 volts right here. So this is where we want our resistance. So right here is where we choose our value. Oh, it even says right here, select 15k ohms R8 for 45 volts VCC. Okay, there it is right there. So this R8 we need to be at 15k. And let's see where R8 is on the schematic they're talking about. This one here, 15k. So if we look at pin 8, pin 8 comes up here. Pin 8 comes up here and connects to this resistor. And they have a 4.7k going to VCC. We wanted to change this to a 15k. So from 4.7k to 15k, let's do that right now. Alright, iron's warmed up. So this here, so if we're changing this, so you can't just build this kit out of the box and expect it to work. You have to adjust it to your needs. That was my point of all that rambling that just previous. So it's a 15k resistor. Let's solder it in, and then we're done with that part of the modification. Let's see here. Alright, so that one's done. Now, the next part of the modification is we need to figure out this coil resistance. Let's do these same calculations using a 24 volt relay. Because if I reduce the current from 44 milliamps to 22 milliamps, this is going to go down. And I can use a smaller resistor. So let's recalculate this. Let's go with 24 volt relay. So let's do this again. 44.2 minus 24 equals 20.2 volts. And our current for the 24 volt relay was lower at 22.1 milliamps. 22.1 milliamps. It's 20.2 volts. 0.0221 times 20.2. And we can get our dissipation of our resistor down to less than half a watt. And if we used a 1 watt resistor, that would be great. So let's figure out the resistance value for using a 24 volt relay. So we need to drop 20.2 volts across an unknown resistor and have 2 milliamps across it. So R equals E over I. So if we go 20.2 divided by 0.0221 equals 914 ohms. And the closest standard value for a resistor is 910 ohms. And I think I'm going to go this way. I'll install a 24 volt relay, and then we can install a 910 ohm resistor in this position here where they have a 47. We're going to put a 910, and then we'll install. Okay, this is going to work out. Okay, I don't have any 1 watt, so I have this massive 3 watt resistor. This will work. Let's just put it on the board and solder it in place, and that's what it's going to look like, which is fine. It's off the board. So let's solder this one in place, and we'll run with this 24 volt relay coil. Now you can't just use one of these kits out of the box for your amplifier receiver, because you need to know what your power supply is going to be and adjust accordingly. This chip is really not marked for pin 1. It's got printing on this face and this beveled edge. I'm assuming the left pin is pin 1, but there's no dot, there's no indication. On the legitimate NEC chips, they have the corner beveled. This one doesn't. I'm just assuming that's pin 1 on the left. I'm going to install this, and we'll put this together. It's not ideal. This resistor's not ideal because it is kind of blocking the... Yeah, we'll work through it. We'll figure this out. Let's just install this chip, solder it in place. And these 1237 chips are cheap. You can get them on eBay, AliExpress. They're not going to be legitimate, but they're going to work. Okay, let's do some of this other stuff here. Let's get our resistor. This is our IN4007. Let's put this in here. I'll use it as a power supply in series with the power supply, just because we can. There's no advantage to having it there. It's just going to drop the supply voltage by 0.7 of a volt. Now we need to figure out these 10K resistors. Which ones are 10K? This is 10K, I believe. Let me check this. 10K. Check the other one. 9.8K. Oh, they're close. So what I'll do is I'll populate this board, get everything built. I'm gonna you don't have to sit around and watch me solder little parts in. And then I'll bring you back in when I'm ready, when it's ready. Okay, there it is, it's built. I decided to ditch the original capacitors and go with some Nichicons, and they're a little larger. These are 63 volt, doesn't matter. And then we made our adjustments to the 2 resistors that count, the power dropping resistor and the relay dropping resistor, to fit our application better. I'll clean the back of the board a little bit. And this is our inputs here, left in, left right, left and right in, and then this is our outputs. And probably won't use the ground here. Alright, we got our little protect circuit built. Let's test it. Let's make sure it's working. So I just attached a wire to the positive input. It says AC 12 volts, but we're going to go feed positive voltage in through this diode, and it's going to power the circuit. I'm not going to use AC on this. I'm going to tap it directly off the B plus of the amplifiers, which is 40. Well, I measured 44.2 volts. So I have a power supply here that's 45 volts. Let's connect it up, and let's power this thing up. I'm just going to ground it. and we hear it click. Clicks rather quickly, within 1 second. That's our power on delay, 1 second for the speakers. I was kind of hoping it'd be more like 3 or 4 seconds. We could probably change that if we adjusted some values of components here. So let me think about that. Yeah, I'm not happy with that. Okay, so let's connect this up, turn it on. What's going on here? Bad connection. Sparking. Sparking because the capacitor needs to charge. Alright, so let's power it on. I'm feeding it 44.8 volts and it's consuming 26 milliamps. The whole thing's consuming 26 milliamps, so if we go 44.8 times 0.26, we're going to get 1.16 watts of power. This thing's going to parasitic power this thing's going to draw from our amplifier, which isn't too bad. 1.1 watts. It's really not going to affect the power supplies since it's going to be tied to one channel. It's just going to make a 1 watt draw on the one channel power supply, which is okay. I don't mind that. So if we check here, let's get a voltmeter, check the voltage drop across our main resistor here. So we got 19.2 volts drop across here at 910 ohms. I think if we do the math on that, let's do the math quickly. So we got, what was it, 19.2 divided by 910. Should give us 21 milliamps times 19.2, 400 milliwatts across this resistor. This resistor is going to barely get warm with 400 milliwatts. I can feel it warming up already, which is nothing. If I had a half-watt resistor here, we would be pretty close to its limit, and it would be getting quite hot, and it might scorch the board, and its life might be shortened. That's why I wanted to put a bigger resistor in here, 400 milliwatts. Yeah, and then the rest of the power is going to be dissipated by the relay coil. Let's see what our voltage is across the relay coil. It should be 24 volts or close to it if everything's balanced out properly. So let's have a look. There we go, 24 volts. Everything's fine. So for a 44 volt supply, our 910 ohm is the correct resistor to use for a 24 volt relay. If I had a 12 volt relay, this resistor would have to be different, and the current consumption would be quite a bit different too. It'd probably be double what it is now. That's why I wanted to switch relays from 12 volts to 24 volts, just to reduce current consumption and power consumption of the amplifier, and keep that as low as possible. You have to keep that in mind. Now let's test out the function of this protect circuit. Let's put some DC on the inputs of the board here coming out of the amplifier. Let's connect up some DC. Alright, so what I did is I connected up a variable resistor, and this is connected up across the 44 volts, 45 volts, and then the slide is going to be this black wire here, and I can adjust, if you look in the meter, I can adjust the DC. This is like a voltage divider, and I can adjust it. So this is on the 30 volt scale. We now have about 24 volts here. I can turn it up and down. I can zoom in. We can make this go to 0. So let's connect this voltage, this DC voltage that I'm generating, up to one of the inputs. Let's see if I can do this. And these clips are not cooperating. And let's connect this up. This thing's powered on right now. It's latched. The relay's latched on. So let's slowly ramp up our voltage, pretending this is our speaker line, and all of a sudden we have a DC offset. So let's turn it up. There, it clicked off, just over 1 volt. Let's try that again on another scale. Okay, click back on. Let's turn it up. Clicked off again. So we're just under 1 volt. It clicks off. Back to 0. I didn't hear it click, but I think it did. Let's turn it up again. Right there. Probably about 0.8 of a volt. Turn it down, it clicks off. So our circuit's working. Not happy with the turn on delay. We could probably change that. 800 millivolts DC. It protects the speakers, which is fine. I'm going to leave that alone. I think the circuit's ready to go. I might change the turn on delay though. That's the only thing I'm thinking about. Okay, here it is in the data sheet. Time delay from power amplifier power switch on to relay on. So that's power on mute. Is determined by this time constant between these two components, C7 and R7. And the voltage on pin 7 is your trigger. So if we look right now at pin 7, you can see we got a 56k ohm resistor and a 33 microfarad cap. Actually, this right now is a 22 in my application on my board, and this is a 56k. I believe it is. Pin 7. Yeah, pin 7's here. No, pin 7's over here. I'm looking at it wrong here. Yeah, pin 7. Pin 7's right here. Goes underneath, and it goes to this 56k resistor, which ties to the power. Okay, so this 56k, we could either change this to something larger in value, like 100k, or we can change this cap to a larger value as something. I'm thinking I'm going to go 47 microfarad, and that should probably double the time from about 1 second to about 2 seconds, which would make me a little more happier. So I'll replace this 22 microfarad with a 47, and we'll see that. If it still doesn't change, we can also increase this resistor to slow up the amount of time it takes for this voltage to build up. Alright, replace that cap with the from a 22 to a 47 microfarad, that red one there. We're going to see how much our turn on delay is now. It's going to connect it up, and it should be around 2 seconds. That's even better. I think we have a little more than 2 seconds. I think it's more like 3 or 4. About 3 seconds. That's just perfect. Okay, and leave that there, and I think we're done. So 3 second turn on delay, 800 millivolts DC on here. It shuts it down, protects the speakers, and protects the amp. So it's good. Okay, so we don't have much room here. Well, we got lots of room, but just where are we going to put this thing? This is intended to be bolted directly to these, but that's not going to work. I think, what do we have here? We have about 40, well, we got about 42, 43 millimeters of depth here in this area, this cavity, and the board is only about 37. So we got clearance. What I was thinking of doing is mounting this board, get a couple L brackets and put it on those 2 screws, and then just use the ground connections as a mounting, and we could do that. Interferes with that cap a bit, we can move that aside, that's no problem. We could do it on this side, but we're running into this terminal strip. Let's try it right here. Just make a couple L brackets, have them stand right up. Can connect our one speaker here directly with a short piece of wire. The other one can go over to here. There you go. I think that's what we'll do. I'll have to make up a couple of brackets. I don't think I have anything that's suitable, but we'll figure it out. We'll make it fit. And then all of this is coming out because I have plans for that too, and that'll be upcoming in the video shortly. going to remove a lot of this mess, the spaghetti mess, and we're going to tidy it all up, and then we're going to simplify this amplifier. We're going to make it run a little more efficient too. We're also going to eliminate these two circuit breakers. They're not going to be useful anymore. So we'll leave them in place, and we'll just route our wires around them. Let's focus our attention to the power switch. I want to redo this power switch. I want to put it right here where this lamp is. So let's do that next. And I got a choice of options here. The switch here, you can see it's like a micro switch, and then it's in this housing. And this actually is illuminated because these two wires here coming out the back will light up this ring. So when it's turned on, it illuminates. Turn it off, it doesn't. And then here's our switch contacts back here. This one work, but it's awfully big, and I don't know if I have room here to drill this out. And also, where's the nut? There should be a nut with this. Paid a lot of money for this switch on DigiKey, and it didn't come with a nut. Are you kidding me? Unless it's somewhere I didn't see. That's a disappointment. And then I have these ones. I have 3 sizes. These are power switches as well. All 3 of these are illuminated. This one's a little too tiny. You have to kind of use your tip of your finger to get it to function. Okay, so that one's out. So it's down to these 2. And I'm beginning to think this one here might be the one. That one's a little too large. So let's go with this one. 220 volt rated. Okay, so these 3 connections here in the center, that's going to be our switch contacts, and then we have 2 on the outside. That's going to be our LED to illuminate the power switch. And it comes with a nut, which I'm happy. So we'll just have to drill a hole and mount that. So let's do that next. Somebody just had these wires tacked on. They weren't. I think somebody replaced this bulb. That's what I'm looking at. It's like this red tape. Let's open this up. Somebody replaced this bulb. Okay. I'm always curious of doing what the previous techs have done. Look at that. So what do we got here? Yeah, somebody replaced that bulb, and I think what they did is that's a 22K resistor in there. You can see red, orange. I don't know if you can see that, but it looks like they had too much current going through this neon lamp, and look what it did. It just totally cooked the inside of it. When you put too much current through a neon lamp, they have a very short life, and then they go dark. So this lamp was working, and I saw it was on, but it was so dim you could barely see it. Now I know why it was dim, because somebody put the neon lamp. There's different neon lamps for different currents, and looks like they substituted the wrong one here. It's just tacked in place. So this is what's left. So I'll have to remove that. I could just break it and remove it, but I'm just going to see if I can get it out without breaking anything. I'm just going to try and get this. It's like a press-on thing. See, just like that. Just try and work it out. Yeah, I don't have the patience to walk that thing off, so I'm just going to break it. It's like a steel clip. Just snap it. Unless I pull it off like this and just destroy it. There we go. That's better yet. I don't think I can use that again. Maybe you can. Here is the original bezel or lamp for that. So somebody cut that, separated it, and replaced the bulb. So you do what you got to do, I guess. I don't know if that's useful in the future. Probably end up throwing it away. So we got our hole. We'll have to drill it out to the proper size now. So I'll do that and then I'll bring you back in. The hole size I need to go for is 5/8, and then I'll just use a step bit like this to hog out the aluminum face, and then we'll be there. Just looking at the switch here, and so these 3 terminals on the back that are in the center, that's your switch contacts. Where is it? Doesn't say. Oh, normally closed, normally open. And then C, this is C, common, normally open, right here in the center, and then normally closed. So pushing that in, these 2 bottom ones here will be in contact with each other. So that's the ones I want to attach my wiring to. And then I was looking at the LED portion of this. These 2 on the outside here are for the lamp. And it is an LED, but I thought there would be just an LED, but no, they have a series current limiting resistor. And this says here, right on it, it says 220 volts, BR. And I think this lamp is wired for 220 volts inside here. So I got, on the power supply, I got 61 volts between these 2. So let's connect it. And I'll show you how it lights up on 60 volts. You can barely see it, it's not very bright. But it is working. That's the 60 volts. Doesn't draw any current or any that measures on my power supply. So what I could do, I can do one of 2 things. I can feed 120 volts here from the mains, and that should illuminate the lamp, or I can pick the voltage off the plus minus VCC supplies. Plus and minus 44.1 is probably 90 volts DC, and I could put 90 volts across here and it'll go a little brighter than what I just showed you, or I could do the 120 volts. I think I'll try this out on 120 volts and see what it does. I don't like feeding AC into a little LED like that. Alright, so what I did is I took this little lamp that was in this switch and I connected it to 120 volts AC, and it glows with a nice brightness. It's got a nice intensity. I think I'm just going to go with that. I'm going to connect this lamp directly to 120 volts so that when it's powered on, it'll be illuminated. Shut it off, it's off. Okay. And then I attach some wires to make soldering easy, because once I install this, it's going to get a little difficult to do soldering. So let's put our nut on. And let's secure this switch in place and see how it looks. Okay, this is going to work out good, I think. Need to figure out a way to tighten that nut. Make sure it's straight, so I'll just use needle nose, I think. Make sure we're straight. Keep going. All right. I think that looks a lot better. I don't know if you can see that. It's going to be our new power switch. So I'll go through and wire this in. One thing I want to add is a suppression cap on the contacts of the switch. And then I also want to add a probably about 3.3 meg bleed resistor from line to ground chassis. I noticed this one doesn't have one, and it's kind of necessary to keep static buildup because everything on the secondary is isolated from the primary, and there's no bleed for any static. If there's any static buildup on between the two, there's no bleed for that. So that's why you add the 3.3 meg resistor. Alright, here's a look at the finished mod I made for the power switch. So power came in on this black wire here, goes straight to the fuses, which is kind of wired incorrectly. It should go to the back of the fuses, not to the front, but whatever. Then the other line came to this lug here, which went to this gray wire. This gray wire goes out to the two thermal switches on the heatsink and returns on this switch and this switch. These are switched from the thermal cutouts. If the heat gets too high on the heatsink, the switch opens, which cuts power to either this transformer or this transformer. That's got the green and pink wire here. And that goes back to this lug and this lug. And then it goes to these two wires here for this transformer and these two wires here for this transformer. So I essentially just moved this black wire from the center here because it was wired permanently on, right? And I moved it to this unused lug. And then I just installed a switch between these two lugs. So the two red wires is the switch. The yellow wire is your lamp. So I'm picking off power from the other side of the line cord for the power for the lamp. And then the lamp is switched on and off with this switch as well, which comes from this side of the line cord. So when you push it in, it lights. When you take it out, it drops. And then I added a 220 nanofarad cap between the switch contacts. I wanted this to be smaller, but I didn't have any caps that size. I wanted to put 100 nanofarad, but I didn't have that size. So let's cross the contacts right here, and then I added a 3.3 meg ohm resistor to ground the chassis. This is a static discharge bleed resistor. All right, moving along. Next, I want to tackle this power supply in this thing. I'm going to eliminate these caps and get rid of this. This is somebody else's work. They just kind of slapped caps in here and zip tied them in place. I'm going to do something completely different. I'm going to eliminate all this. I'm going to eliminate the bridge rectifiers. I'm going to get rid of all the spaghetti wiring. And I'm going to mount a printed circuit board here. So I did get some delivery yesterday. This actually didn't take too long to get to me. It's probably less than 2 weeks. So what we got here? What we got here is some bare copper boards, and this is just a ticket. Okay, so this is 100 millimeters wide. Let me see. 100 millimeters, and that'll fit and cover up these 4 holes. That's basically what I'm trying to do here, is cover up these 4 holes. I'm going to mount a printed circuit board here. I need to determine how long it needs to be. I think it needs to be about 120 millimeters, and I'll have to cut this down a little bit. But my plan is mount this board here. I'm going to draw out a circuit, and I already started here. I got to measure these exactly where I want to place my capacitors, because the capacitors are going to be mounted on the other side through onto the printed circuit board. And then I'm going to incorporate the bridge rectifiers right into the circuit, and then use surface mount rectifiers through hole capacitors, and this whole board will replace all this mess. So I need to cut this to length, and what I'm going to do is I'm probably, instead of doing photo etching or toner transfer method or anything like that, I'm going to build the circuit on here with tape. I'm just going to tape it out, and that's probably the quickest, easiest way of doing a simple circuit like this. Just tape it out. Wherever there's no tape, the etchant will remove the copper. So I'm going to get busy on this. I want to finalize my design here. It's probably not going to look like this. It's probably going to look a little different. I'm going to use thicker traces. I do have, let's see what kind of tape I have. This is probably 10 millimeter tape. Probably make my traces 10 millimeters wide. Thing is, with these surface mount rectifiers, you want to have a lot of copper surface area around where the rectifier is mounted, and that's your heat sink. for that rectifier. Instead of having a thing bolted to the chassis, it's going to be soldered to the soldered to the copper pad, and that's where the heat gets dissipated. So I'm going to redesign this a bit. I'm going to thicken up all these traces. Probably this basic layout's going to stay the same. So without going into too much detail on what I'm doing here, I'm just going to show you basic steps. So basically what I did is I cut the board to size 10 centimeters wide, 12 centimeters long, and I mounted it where I wanted it to be, its final positions, and then I marked the 4 mounting holes and I drilled them. The reason I want to drill these and figure out where they go, is so I can avoid those areas when I start taping off my traces. So now I can remove this board and we can start taping out our circuit. I think I got this to the point where I'm ready to start etching. So you can see it's a pretty simple circuit. I didn't spend much time. I put about 10 minutes in taping this out, and then I cut out the areas where I didn't want copper. And so this is, the capacitors will go in this spot right here, and right here, but they'll be on the other side, right? 4 of them, because there's 2 power supplies on this. The rectifier diodes will be on these 8 spots here, and they'll be doing their rectifying. These 4 big pads here in the center, this is going to be the AC input from the transformers, and then we have our DC outputs, positive and negative, here and here. It's a pretty simple circuit, and I kind of followed my layout a little bit, but not too closely. I just wanted to make sure these traces were nice and thick so they have lots of current. And we got the tape on. So let's etch this. I'm just going to use ferric chloride, and I'm going to use probably a Pyrex dish or a Corningware dish, and I'll just put just enough on there just to do the job and etch that. And I'll put this on a hot plate too. It's kind of cold outside. We're about +5 degrees Celsius, and etchant works better if it's warmed up. So I'll warm it up to about 50 or 60 degrees Celsius, and this will etch really nice. Just about done. I didn't expect it to be done so quick. You can already see the traces through the fiberglass. I guess I really didn't need to heat it. It was so quick. I didn't use very much, probably a couple ounces of etchant. Let's see what we got here. Let's see if we can get another look at this. Yeah, we're just about done. Keep that going for a few more minutes. It's been less than 10 minutes already. Maybe this Chinese boards, their copper's so thin. Maybe that's what it is. And it is done. Yeah, it's done. Okay, turn the heat off. Here's what it looks like. Have to rinse it off. I'll wash it good with tap water. I'm just getting the most of the etching off. 99% of it, and then I can wash this. Look at how Actually, it turned out really nice. Okay, so let me wash this and then we'll start drilling our holes. All right, back at the bench. I was really pleased with that. That turned out really well. It was dead easy too. Very easy to tape it out. And then all you do now is peel off the tapes and reveal your copper traces. Now I'm kind of, oh, these coppers are thin. I should have done my homework better when I was buying the boards, because this isn't 1 ounce copper. Let's see what this measures here. 0.54. Let's measure the copper. 0.54. How does that work? So bloody thin it doesn't register? Wow, is that ever thin copper? And I can feel it. It's very, very, very thin. Yeah, I should have done my homework better on that boards I bought. But this will work. The only thing, it won't have the heat dissipation for the diodes like I was expecting. Let's peel all this off. And then can start drilling holes. What I can do is this capacitor, this is the caps I'm going to be using, 50 volt, 10,000 microfarad, Nippon Chemcon. These are 10 millimeters apart, so I could just use this as and mark it with my eyeballs and just scratch the copper right where I want the holes, and I can just drill 2 holes, mark these out. I'll get this drilled, take off this. Signed my work. Anybody else sign their work? I always sign my work. A lot of guys that do guitar amps and stuff sign their work. Alright, now it's time to talk about this driver board. Where do I start? So this is all original except for a few things. Somebody replaced the caps. Somebody replaced Q703 and 704. What they did is they installed a pair of BC 140s. I don't know if you can read that. Transistors. So they removed for whatever reason, they removed the originals and replaced these two. And everything else is original. The pre-driver, Q704 and 703, are the ones that have been removed and replaced. Now, I was looking at for this circuit here, and from what I gather, let me back up a step. This complete circuit that Harman Kardon uses for this amplifier was taken out of an RCA manual, and for the most part, here's the RCA manual and the diagram. So for the most part, it's identical. Now they have on this circuit, they have these 2 transistors here in the middle, and they call it the protection circuit. I'm not sure what this does. I have a feeling it clamps at during peak. So that's what that is, and that's what this is drawn here. Basically, it's just reproduced. And so if you wanted to add this circuit, you could. Don't know what benefit it's going to give you. This alone works pretty good as the way it is. It produces, 75 watts, what I measured. But I'm not going to be adding that circuit. This, though, I need to determine why we have that glitch on the right channel, and it looks like it is only on the negative cycle of the waveform, which tells me it's probably one of these 2 transistors here on the negative side. So it could be the driver or it could be the output, and I'm suspecting these 2 guys here. I'm going to pull all these transistors out and test them out of circuit. Another thing I'm going to do is I'm going to pull these differential pairs out and test these, make sure that they match. Basically what I want to make sure is that they're not flaky and that they match in gain. And then I'm going to take a look at these BC 140s as well. This little guy here, this is Q708. That's the bias transistor. Bias transistor could be a 2N5232. So we can look at this one as well, and we can check all the specs out. I'm also going to lifting resistors and testing their value, replacing the caps. So let me get busy on this, and then I'll bring you back in if I find something that's worth talking about. Just going through and checking these transistors. These are the driver transistors. This is the, which one is this here? This is the left channel. This is the NPN transistor driver. You can see my connections are a little touchy. But I just heated the transistor up with my hot air station. Now let's spray some cold on it. You'll see the dramatic change in characteristics. Watch. As I spray cold on it, you can see it collapses in HFE, and then as it warms up it kind of expands again. Mainly what I'm looking for is twitchiness, like if the waveform collapses and shows any glitching. That's what I'm looking for. But I don't see this. I don't think I'm seeing anything here. Spray some more. Kind of changes characteristics, so you can see how it changes when you cool and heat a transistor. I'm going to go through and check the other three. I might end up replacing these transistors because one of them is low in gain of 73 HFE. The other one on the other channel is 108. It's quite a bit of difference. The PNP is not as bad. One channel I got 97, the other channel I got 103. So there's not much of a spread between those two. But the NPN, we have quite a bit of a spread. So this transistor is wigging out. This is the voltage amplification stage. This is one of those BC 140s that somebody placed in there, and it's doing weird stuff. If I replace, let me put the transistor from the other channel in. I thought maybe it was my curve tracer with a dicky connection, but let me put the other transistor in. And it comes back solid. Yeah, so this is really suspicious here. Very, very suspicious. Now I did heat this transistor. This is the good one. I'm going to heat this one up and see how the characteristics change. I don't want to heat it up too much. It's about 140 degrees Celsius. It cools back down. Burn my fingers. Give it a little spray of cold. Okay, that transistor seems okay. Let's go back to that other one that I found. Problem is, I don't remember which channel I pulled which transistor out of. I wasn't really paying attention for these ones. Yeah, look at this. This transistor is done. Let me heat it up. Got a bad connection inside it. Bond wire, or doesn't want to. Yeah. It's definitely a problem. You cool it down. Yeah, didn't like that. So yeah, I'm pretty sure that's my problem with that right channel. Okay, so I was glad I found that. So the original differential pairs, I'm going to put these back in. I'm going to put the 4 drivers back in. Even though one of them is low in HFE, this one's 73, it's the outlier, and the rest of them are around the 100 mark. I'm going to put these 4 back in. Somebody put these 2 in, these BC 140s. And this one here is the culprit. It's got a gain of 57. And this should be pretty simple to replace. It's a pre-driver. I'll have to check the specs on the pre-driver and what it needs. Should be fairly easy to substitute. And I'm going to pull out these 2 bias transistors. There's one here and on this side. I'm going to pull these 2 out and test them while I got the machine out so I can do that. and then everything will be good. Alright, so this is ready to go. I have finished everything on this board, and it's yeah, it's ready to drop back in. So went with the old long tail pairs. Those are staying. I subbed in a couple of 2N2102s transistors for the ones that were bad. I replaced them with these. Give it a vintage look. These are T05 transistors out of my vintage transistor stash. Tested them out, they're good. Okay, what I got here is a Schottky diode, and then I have a standard bridge rectifier diode. And I'm going to solder them both down onto the board. I can remove this one later and put a Schottky in its place. But I'm going to use solder paste and hot air. So we're just going to solder these in place. And it moved on me. Can't have it there. It sure wants to move. Okay. Let that cool down. The reason it wants to float around is because there's no solder mask to hold the solder paste in one position. So let's see what we got here. What's going on here? Okay. Once it cools down. Alright. I'm going to tack some wires on here so we can put some current through this, and then we'll do some measurements. Okay, everything's cooled down. I tacked on some wires. Let's check the voltage drop across each diode again one more time before we put current to it. So here's the Schottky. I got it backwards. 2.6, and then the regular rectifier 4.8. Okay, so this reverse. We've got open. Open. Okay, so let's put some current here. I got a current limited power supply. Let's put some current across this. Okay, I'm going to ramp it up to about 1 amp. So there's 1 amp. Let's measure the voltage drop across each diode. So on our regular diode, we have 820 milliamp volts. On our Schottky, we got 399. So it's more than half. More than half. So this is more than. The efficiency here is quite a bit better. Let's turn up the volume. Let's go up to 2 amps. 2 amps. $437 millivolts, and on our regular diode, 850. Let's go a little higher. Let's go up to 4 amps. I think my power supply goes up to 5 amps max. Okay, 4 amps. Schottky's got 487. This diode is actually doing a lot better than I expected. So even this, we still have half. So let's do the calculations on this. 480 millivolts. So in this we got 4 amps times 0.48. So we got 2 watts of dissipation almost on this. And it is getting hot. Put my finger on it. Ooh, that one's worse. So what was this again? This one was... let's go 840. So 3.66 watts. 3.36 watts. So you can see the Schottky is a little more efficient, and that's why I picked it, because efficiency. Now, lower voltage drop means higher rail voltage. Higher rail voltage means higher output on your power amplifier. That's basically my reasoning behind getting this way. So I'm going to populate this with 8 diodes. We're going to make our bridge rectifiers, and then we'll install this in the amplifier, and we'll test it out. Alright, so I got the 8 rectifier diodes, Schottky rectifiers installed. I'm also going to install some 100 nanofarad MLCCs across each rectifier, just to suppress any noise that might be there. I'm not saying there is noise, I'm not saying there isn't, but I'm just going to put it there as a safety thing. These caps are cheap, they're 5 cents a piece. So for an extra 40 cents I can protect our power supply from making noise. So I'm just going to solder these in and get these in place. Now, I was going to do a whole rant about different rectifiers people use on upgrades for audio equipment. I hear a lot of noise about these hex freds. I was going to do a long rant on this video, but I decided to cut that all out because this video's got long enough as it is. I'm going to solder 7 more of these in, and then this board is going to be ready to go into the chassis. Yeah, these capacitors are 100 nanofarad at 200 volts, so they'll be more than adequate for this application. The diodes themselves, they're rated at 120 volts. Kind of low. I'm not pleased with Schottky diodes. Schottky diodes are hard to get in high voltages. That's the problem. That's why they're so not being used widely right now. But if you can find a high voltage Schottky diode, use it. But 120 volts, and this should be adequate for this power supply. Problem comes when you have transients that come from the power line through the transformer and onto your rectifier, bridge rectifier. It can cause problems, voltage spikes, can knock out a rectifier, and then you have a dead short, and then you have a blown fuse, and then you... So we'll see how this works. This is all experimental, but I have a feeling it's going to be a good upgrade. Okay, just one final test before we install this. I just want to go through and check all our diodes, make sure that they're all good and in place. We've got no shorts. Okay, I'll put this in and then I'll bring you back. We'll show you what it looks like when it's finished. Alright, just going through and redoing the power supply wiring and getting things installed. And I discovered something very interesting. And this would explain a lot of what I experienced before I even started. Have a look at this. I don't know if you can see this. It's not even soldered. This one's soldered, this one's not. That is the base connection for one of the output transistors. So that would explain why I was getting a corrupted signal. It is not soldered at all. There's no solder on that. It was wrapped and crimped, ready for solder, but it wasn't soldered. It's loose. Well, it's loose now that I manipulated it, but that's really interesting. So this fault came from the factory. Oh, what would that be? 40, 60 years ago now almost. And it probably plagued the owner for decades. We don't know. It could have not made any noise for a long time. If that was wrapped around there and crimped, looks like it was crimped because that pin is kind of crushed. But here, let's just fix that right now, and we'll call it fixed. Surprising that got through quality control. There we go. So here's a look at how far I've progressed today. Got the board in, like I soldered the rectifiers on, soldered the suppression caps on, got the board in, got it all wired in. The blue wires is my negative supply, the red wires is the positive supply, and then all the transformer connections to the center. Ground in the center. Pretty easy, pretty nice. I think I like this. I'm just hoping these rectifiers hold out. Now, what else did I do? I installed the protect circuit. I haven't wired it in. I just ran the power wire to B+. I still have to wire in the speaker connections. And that's about it. I'm going to replace these two caps, but I want to get rid of this monster. It doesn't need to be 250 microfarad. I don't know why they chose such a large value. If I look on the RCA manual in the schematic, they have an input capacitor C1. And if I go down here, C1's a 5 microfarad. And that's adequate for an input capacitor, a blocking capacitor. I could probably go, I have some 100 microfarad bipolars, I could probably use one of those. What I want to do is get rid of this arrangement. I want to put a shielded wire, this 4 inches, I want to shield it, and then I want to have my cap right next to the ground here. And have this all shielded. These purple wires here are grounds, and it kind of shields it if I, you know. But I want to make sure this is really good. Here's the top side. I know, stubby capacitors. These are 10,000 microfarad at 50 volts. Now I could put any size I want in here now. This is easy. I could remove these. I could put, let's see, what else do I got? 8200, 12,000. I got 22,000. You got lots of room for a bigger cap, but I think these 10,000s are sized properly for this amplifier. Find out on the power test. And I also removed the 4 transistors, repasted the heatsink compound. Here's a look at all the stuff I removed from underneath. 2 bridge rectifiers, 4 caps, a bunch of janky wiring. Alright, everything's back together and we're ready to do our first initial adjustments. So I'm just going to connect the voltmeter across the output. And we're going to just monitor the DC offset. There's no adjustment for it, and if it's really too bad, too high, we're going to make some changes to the circuitry to fix it. So for right now, we're just going to monitor it, and then we're going to do our bias adjustments. So let me get this connected. And this is our bias meter, this fluke. So we connect our 2 test points here, right here beside this resistor. We'll just connect these up. And we have, this is our bias, this is our DC offset. And you can see everything. Okay, let's turn it on. Here's our power consumption. You can see that. Let's turn it on. Relay click. It's a very quiet click. You've got almost 200 millivolts on the output. Okay, so we want, for this value, we want between 8 and 10, or no, sorry, 8 and 13 millivolts. And we are up at the high end. So I'm going to turn this to about 10. Careful not to short anything out here. I'm just going to turn this down to about 10. Alright, I'll leave it there for now. If it changes, it changes. Okay, we still have 165 millivolts. Power consumption dropped 26 watts. Let me reconfigure this for the other channel. Alright, other channel, we only got 6 millivolts, and we got 117. So let's adjust this one up. Go the other way. Alright, I'm going to leave it right there. Our power consumption went back up to 27, almost 28 watts. So I'm just going to let this stabilize for a while. Still not happy about this DC offset. We still have 100 millivolts on the left-right channel. It's basically the way it was before I started working on it. So I have a feeling those differential pairs are probably drifted in age with age, and they're showing their limitations. We might have to replace those transistors. What I might do is replace them in one channel, and then we'll see if this improves. Okay, I'm running into some problems here. I was doing some distortion tests at 50 watts, and I'm working on the left channel right now. And I did the 1000 hertz tone, it works fine, and then I went down to 20 hertz, and protection kicked in. So right now I'm at 110 hertz, and I got 160 millivolts offset on the output. Let's turn down the frequency. Let's go 100, 90. Kind of staying stable there at 160. Okay, 80 hertz. Seems like it's kind of oscillating a bit. 70 hertz. So at 160. Okay, let's go down to 60 hertz. 50 hertz. And the protection just kicked in. And it's in protect right now. Relay's open. 177 millivolts. Let's go down to 40 hertz. And it's doing the weird oscillation thing again. 30 hertz. You can see it's going quite high. 20 hertz. For whatever reason, that protect circuit doesn't like low frequencies. We might have to go back in there and adjust some settings. Alright, there's the left channel. That's 20 hertz. Let's go down to 10 hertz. 10 hertz looks alright. So that's 10 hertz, and the protection went on. Okay, let's turn this up. 20 hertz. 30 hertz. 40 hertz. Everything looks good. 50, 60, and our protection clicked back in. So for whatever reason, it doesn't like frequencies below 50, 60 hertz, and we're going to have to adjust that because this amplifier needs to work in that range. We're doing 50 watts here. Okay, let me go back down again. 59, 58, 57, 56, 55, 54, 53, 52, 51, 50 hertz. 49. And it's clicked off at around 44 hertz. Okay, we'll have to look into that. I'm going to check the other channel, see if it does the same thing. If it does, it's probably just that circuit is temperamental, that protection circuit, and we need to make some changes just so it's more accepting of low frequency signals. Okay, now that I find out it's going into protect at approximately 45 hertz and less at 20 watts per channel. It does that for both channels. So I think this circuit is just a little too sensitive. Right now there's a 10K and a 10K and a 100 microfarad cap. I think what I might do here is I might increase these resistors to something like a 33K and possibly change this to 220 microfarad. I'm going to play around with some of these values and I'm going to see what changes. First I'm going to start with increasing these two. Like I said, probably 33K is about a good start point, and then I'll test it again and we'll see. It shouldn't go into protect probably till about 15 hertz or so, or 10 hertz, when it's really at the bottom end and it's really working hard. So let me do that. Let me change those resistors and I'll bring you back and I'll tell you what my results are. Alright, so I changed those two resistors. Now let's do a test. So I got it load, got a signal going in. I'll put you up here, and then we are going to increase the amplitude until we get 20 watts. Should be right about here somewhere. Too far. Okay, so that's 20 watts right there at 1000 hertz. Let's go down in frequency. $60 hertz, 50, 40, hasn't clicked off yet, 39, 30 hertz, still on. $20 hertz, and it hasn't cut out yet. And let's see here, let's go down and see where it cuts out. $11 hertz, we're still on. There, right at 10 hertz. Clicks back on, 11, 9 hertz, it shuts off. So that's perfect, I like that. It's better than what it was, so we can listen to our music and we don't have to worry about cutting out on bass frequencies. Alright, so while I didn't do a power test, let's do our 10-minute endurance. Let's turn this thing on. And we have our load connected, 8 ohm load. Scope is on the screen. Here is my turn up. Turn up the volume. Let's see here, let's find clipping. Okay, we're into clipping there. Let me adjust my scope. Clipping, let's back it off. Right about there. What do I got? .6 volts RMS on the output. Let's let that cook for a while. Turn on our timer, and we'll see how this behaves. I'll bring you back in 10 minutes or sooner. This is our power consumption, 244.5 watts total. Alright, we've been full power here for down near 10 minutes, and I'm actually pleased by all this. I was expecting my power supply here to get a little warmer than what it is, but it's staying really cool. I don't feel much of any heat coming up from the bridge rectifiers. That's what was worrying me the most, because that copper was on those Chinese boards are so thin that it wouldn't be able to carry the heat away from those diodes, but it seems to be working. Or the diodes aren't being stressed enough to get them hot. So let's take some measurements here. 44, 45 degrees on that one. 46 on that one. This side seemed a little warmer. This side says 46. Yeah, 44. It's pretty consistent right across the board. All 4 heat sinks are the same. Well, this one's a little higher. 46, 45. This one's 47. 48 almost. So this transistor is getting a little hotter than the rest, but that's okay. It's actually doing pretty good. Full power for more than almost 12 minutes now. So this is a keeper, I think. I'm going to shut this down and let's try. That was 4 volts going in, by the way, to get that full power output. Let's turn down the volume here, and then let's try some square waves. And then let's see what we can do here. Okay. So we're at probably right around 1 watt output. Square wave, that's 1000 hertz. Let's go down in frequency. Let's go down 900, 800, 7, 6, 5, 4, 3. Two, 1, 100 hertz. It's looking pretty good. 70, 60, 50, 40, 30, 20 hertz square wave. That's pretty good. Okay, let's go to the high end of the scale. All right. 1 kilohertz. 2, 3, 4, 5. All right. 6, 7, 8, 9, 10. 20 kilohertz square wave, which isn't too bad. I've seen a lot worse at 20 kilohertz. Starting to get the rounded edges. Let's go higher. We lose our square wave probably around here somewhere. Right here, let's say, and that's 55 kilohertz. Yeah, get some good specs. Be a nice amplifier. Well, there it is, back together, and I'm done. I think I've taken this as far as I want to take it. Did a lot of work to it. Yanked out the previous tech's work on the power supply and redid all that. Replaced the pilot lamp with a switch. Replaced all the caps. One of these caps was dead. It was this Macron cap. It's 47 microfarad, 100 volts. It was completely dead. I can't remember where this was. I think it was just in hanging off one of the power supply rails. So it wasn't really doing anything other than just taking up space. The 2 input caps, these are 250 microfarad. They measure over 300, and I replaced them actually with a pair of 220s. So that's all good. Bridge rectifiers are redundant. A couple of resistors that were out of tolerance. 1 dead transistor, so I replaced the pair. And yeah, I think it's come a long way now. I think this is quite an improvement over from when I started. I remember we had the right channel was really twitchy and glitchy, and you know, one of these transistors was the problem. And then also we found a solder joint that wasn't soldered from the factory from 50 some years ago. And it's surprising the other tech that was in there didn't see that either, because he was in there monkeying around and replaced all those caps, and he still didn't pick up on that. So it's good we found it. Okay, so this one's going to get a little listen test and then put it aside. I do have the complements to these. I have a Citation 15 tuner and Citation 11 preamp, and those are going to be coming up in the channel. I don't know when. I just wanted to get this one. I just grabbed this one first out of the three, and wanted to work on it. And yeah, it was enjoyable. I learned a lot about these amps. It's a good performer once you get them going, from we saw from the square waves, and I'm going to have fun listening to this one. So take care, and we'll see you on the next one. Thanks for watching.